Amino acids, DNA 2019. Odd one this, what they've done is they've got a chromatography plate, a thin layer chromatography plate, and they've separated out all of the spots. So you can see all the amino acids rise to different points. So don't go left to right, just go up and down for now. Position of the original spot has gone into 3 different spots, which are not dark, they've got sort of light rings. So they've gone into 3, so that position of the original spot is separated into 3. But they weren't happy with the separation. They thought there might be more amino acids. So what they did is they turned it on its side and put the solvent another way around and made the solvent go across the paper. So if you take the top light spot, the top one of the lighter spot, that one amino acid, when the solvent has gone the other way, left to right, so they put the left part, they've turned it round anti-clockwise through 90 degrees, and that top left spot has made one black spot, one darker spot. It's not separated, it's just moved. So that top light spot, when they've turned the plate round and let the solvent go up from left to right, as they've turned the plate through 90 degrees and dropped into the solvent, that top left spot has just moved across to the right and made the dark spots. That's one amino acid. The middle light spot has separated into 2 dark spots. So that middle light spot has actually separated into 2 when you've turned it round the other way. And the bottom left-hand spot has also separated into 2. So you've got 1, 2, 3, 4, 5, and you've got 2 at the bottom that never separated out at all. They didn't go anywhere. So we've got 7 different amino acids, 7 different spots. The bottom 2 spots are slightly confusing. They didn't go anywhere. They didn't rise up the plate at all until you turned it round the other way, and then they rose up from left to right as you turned it round and stayed on the pencil line, but did actually separate them into 2. So basically you've got to count the number of dark spots as it's separated first time and then second time when you've rotated it. A suitable reagent for the hydrolysis of a protein, you use concentrated hydrochloric acid to break the peptide link and put water back in. How do you tell how do you see the amino acids? You use a chemical spray called ninhydrin, or you can use ultraviolet light. We've talked about how many dark spots there were. There were 7. Why it was necessary to use 2 different solvents and turn it round? Well, obviously the person doing the experiment wasn't happy with the separation of the amino acids with the first solvent, so did it again with the second solvent. Okay, we've got 2 different complementary strands in part of a DNA double helix. We've got 2 nucleotides joining together with hydrogen bonds, and you just got to draw the 2 hydrogen bonds. You can identify the 2 bases if you wanted to at the top as adenine and thymine, and the 2 bases at the bottom being guanine and cytosine, but all you've got to do is draw the dotted lines in. I would prefer delta pluses on the H's of the NH, and I would prefer lone pairs of electrons on the O's and the N's, because it's the attraction between the lone pairs of electrons on the O's and N's and the delta pluses on the H that actually form the hydrogen bond. I've taken that from the mark scheme. It doesn't seem as if it's necessary, but it would be preferable as far as I'm concerned. Next, it says draw a ring around each component part that makes up a cytosine nucleotide. So a nucleotide has got 3 parts. It's got a phosphate, so you need to draw a ring around the phosphate. It's got another part, component part of a nucleotide is that it's got a 2-deoxyribose and it's got a base. So you have to identify the cysteine base, which is the one right in the middle of the screen, and it's 2-deoxyribose that it's joined to and a phosphate that it's joined to.